Shinnis, and I'll be taking us through some examples of building PARC models. There are two flavors of PARC model. One is a PLS, one is a PCA, and we'll build one simple example of each one of those. We'll start with PLS model. PLS stands for partial least squares, and it's a linear model. The purpose of a PLS model is to simulate or model a single system parameter from a set of other system parameters. For example, if you have an instrument that is sometimes unreliable, but you have a span of time in which it was very reliable, maybe you can simulate or model that parameter from other system parameters so that when it does move into an unreliable state, you have a model that is simulating or approximating what that instrument would show you. So you'll have one system parameter, a y, and all of the other parameters are referred to as x's. This is the mathematical form that the PLS model takes. Your single y is approximated from the x's by multiplying each by a coefficient and adding an intercept at the end. This is as in-depth as we're going to get in the math because I am not a mathematician, but you can see that it's a linear model. There are no powers. There's just x1, x2, and their coefficients. Now, since PARCModel is launched from a trend, the way you build the trend affects how PARCModel interprets those tags. So when you're building a PLS model, it looks at the top tag, the very first tag on your trend, and interprets that as the tag you want to be your y. All of the other tags on that trend will be the x's. So PARCModel will try to use those tags to model or simulate the first tag. And we'll see that when we build our example. Some ways that this might be used are simulating flow from either valve position or DP, delta pressure, or power on a pump. An example where I have used this in industry has specifically been modeling flow from pump amps. We had a condensate tank, for example, that the flow would drop below the reading of the instrument and it would just read 0 even though the pump was pumping condensate. And so what we did is we used the periods of time where there was a flow reading and we modeled that flow based on the pump amps. Created a model of that flow so that when the flow itself got so low that the flow meter wouldn't register it, you still had a model of flow based on the pump amps because the pump was still pumping and registering amps. Another example are discrete test results modeled from a set of continuous process measurements. There may be something that you only test every 4 to 6 hours, but you'd like to know between those tests if you're approximately online or you're approximately the same. Well, if you have continuous measurements that can be used to approximate that value that you're going to test in the next 4 to 6 hours, you can build a model of those discrete test results based on what those readings were when the test sample was taken. So you can build a model that way using PLS. So we're going to do a demo now. We're going to build a model of flow based on DP. So I'll exit out of presentation mode, shrink this guy down. And in the interest of time, I have my trend already built. You can see that at my top tag, my first tag is flow. That is going to be the variable I want to model, that I want to predict, that I want to simulate. So that is my y, the flow. Now I told you that the model, the PLS model, is a linear model. So if you want to include any nonlinearities, for example, flow is directly related linearly to the square root of dp, not to dp itself. So what I've done is I created a calculated tag where I subtracted the downstream pressure from the upstream pressure, but then I took it one more step and I just took the square root of that difference. So now I should have a very good fit between these two tags in a linear fashion, which is set up nicely for PLS. So I have square root of dp as my second tag. I have specific gravity as my second X tag or my third tag on the trend. I just threw that in there just to see or to show that we can put any number of parameters in here, and then we can look at their importance later and determine if they're needed or not. On the right-hand side, I have the same flow tag, but for a different period of time. This will be the period of time we use to evaluate our model to see how good of a job we did at building a model. So you can see the time frame here is January 24th, February 3rd, and on the right-hand side, February 8th to February 15th. It's very important to evaluate a model against a time period that is not included in the data set to determine if the model is valid going forward, because as time goes on, it will be using data that it never saw. So let's get started. You right-click anywhere in the trend area to open the PARCModel window. Most of what is on this screen we're not going to refer to because I'm just going through creating a simple model to get you off and running. The things that you want to look at first are these settings at the top. Auto selection of components, that's more for primary component analysis we'll talk about later. The process type that we're modeling is continuous. Batch is not even an option because we're not using run browser in the back. Really, the only thing that you might want to change is the step size. And I'm going to leave it to 1 minute step size. That's sufficient. Sometimes for flow, you need a much faster step size, but in such a case, as you can see, I'm using 11 days. You wouldn't use 11 days of data if you needed to tightly model a very fast responding flow. So I'm going to leave all of these settings the same, and I'm going to create a PLS model. And when you click create, it's using all of the data that's in that trend that you saw, that entire 11-day time period. So the first thing you want to do when the model comes up is you want to clean up the data, or at least look for opportunities to clean up the data. My eyes immediately go straight over here to the right-hand side, T2 versus T1. Again, I'm not going to try to explain the math behind it because I'm sure that would be a disaster, but I can understand pictures. And what I know about this picture is you want your data inside these circles. If a lot of your data is outside these circles, well, that's not just licensed to go remove the data from your model. Actually, it's an indication that the model is not going to be very good. It doesn't fit the data very well. So maybe there are some tags that are needed in addition, or the time period that you selected is not a good time period. We only have a few observations that are outside. So what I'm going to do is click and drag to highlight those data points, and you see they turn red. The same data points that are represented on this line or on this plot turn red, and over here as well. Now all I do is I press delete key on my keyboard. It deletes them and at the same time recalculates the model dynamically. So now this looks much more friendly. All of our data is nice and tight. It's packed inside our concentric circles, which again graphically says that the model is using, all of the data is fitting the model well. This is a common Y to Y plot. You can see this is the original Y. So this is the values that we had coming from our trend. And this is now the predicted Y. They're plotted against each other. They're very close to that line. And you see our R squared is ridiculously high, which you would expect it to be when you're using flow as a model based off of the square root of dp. So you'd think with that kind of R squared, we're done. There's one more thing I want to look at, which is down at the very bottom, the variable importance. Okay, as we expected, square root of dp is very important, 0.942. These importances will always add to 1. So I think of them as percentages. I don't know if that's correct, but it seems like 94%, so to say, of the model is dependent upon the square root of dp, and less than 6% is dependent on specific gravity. Not surprising. You don't really need specific gravity. So what I'm going to do is I have an opportunity to simplify my model. Yes, the model's good, but if I can simplify it, it may make it a little bit faster. So I'm going to right-click on this specific gravity right here. You see this x2, and I'm going to exclude the variable. Now you can see why I had the variable in there in the first place. When there's only one x and one y, these plots get boring. There's really no statistics to look at. There's no data to clean up. So I left a specific gravity in there so that we would have something to talk about up here. but specific gravity is not needed for flow. And you see the R squared dropped from 0.994 to 0.993, almost no effect. Now I like my model, and I'm going to click Save. So I get a dialog box where I'm asked to give it a project name. I will say flow indicator, for example, 1001. You want to give it a project name that's meaningful, and also a model name that's meaningful. These I typically use for versioning. So I'll call it V1 or V2, or if I've done something very specific, I'll say V1 with a short comment. I'll just call this version 1. And then finally, select as active model. You can build version 2, version 3, version 4, version 5. You can have many different versions of this project, this FI 101, but only one of them will be active. And you'll see why that is important when we go to Tag Browser. So I have my project name. I can add a description if I like. And I have my model name, version 1. When I hit continue, it saves the model. And just like that, we're done. I can now close PARCModel window and open Tag Browser. Because I've created a new model, I'm going to hit refresh. I want my source to be PARCModel. And I hit refresh to make sure, because every time you build a new model, it instantaneously adds tags to this PARCModel source. So I just, as a habit, I will refresh the PARCModel tag list to make sure I have what I want. And you can see I have tags now listed over here, FI 1001, lots of different things. The tag that I want is the YPRED. So I use star YPRED. And you'll see there are two Y prediction tags. There's one specific to my version that I built, and then there's just this overall FI 1001 YPRED. This is where the active model becomes important. If I have version 1, version 2, version 3 of this model, only the active one is being used for this overall Y prediction, Y predicted value. You can always trend any of the individual ones that you want. You can trend them all at the same time. They're all there to be trended. But this allows you to trend a single tag and then change which version is active without having to go touch trends or touch displays or touch Excel workbooks that reference it. So now I'm going to drop this over here on my trend. I'm going to scale it similar to my flow tag. And I'm going to change the color to something that contrasts with blue so that we can see, yes, it falls right on top of the blue pin. So this is a valid test because of what I've done is I've used an 11-day period over here in late January to create the model. And now I'm testing it against data that's in mid-February. So this is data that was not used to create the model, and it's valid, and it falls right on top of it. I now have a good model of flow. That is all for our PLS, and now we're going to move on to PCA model. Not going to save that trend. And let's talk a little bit about PCA before we go to our demo. PCA stands for Principal Component Analysis. And there's all kinds of math also behind each one of those words. But essentially, PCA model is a way to characterize a system or characterize a piece of equipment. There is no Y variable that you're trying to predict. You're not trying to simulate a single variable from a set of X's. What you're trying to do is say, I have a system or I have a piece of equipment, and I want to know if it's shifted, if it's moved into a different operating regime. I want to know if it's a different system today than it was yesterday. That's how PCA is used. So every variable is referred to as an X. It's just an X1 through Xn. Now, when you build a PCA model, instead of trying to predict a Y or calculate a Y from other X's, what you're modeling is each X against all of the other X's. So X1 will be modeled from the values of x2 through xn, x2 likewise, all of the other x's. So a good way to think about it is PCA is developing a mathematical way of showing the relationship among all of the x's. And so in that way, it creates kind of this fingerprint of what the system looks like when it's running. So here's some uses or ways that I've used PCA modeling to diagnose instrument or equipment drift. For example, if you have an instrument in the field that you know scales up over time or it's subject to drift, like a pH meter, for example, something that you have to calibrate all of the time, but you don't really know, is it off? Has it changed? Well, if you have a period of time for which you know all of your instruments were good, you use that as your thumbprint. You use that period of time and say, I'm going to build a PCA model from that. And then the PCA statistics that you trend into the future can tell you if something is shifting. And that's what we're going to look at in our demo. You can also flag significant process alterations. An example that I've seen multiple times is a manual valve that is always open or should always be open gets closed. Well, there's no indication in a DCS or a PLC that a manual valve has been closed. What you see instead and what the operator sees is something is different. The relationships that I'm used to aren't the same. Well, PCA can flag that so that you don't have to wait for a person to recognize the system has changed. PCA will automatically see it and will say, oh, something's changed. It doesn't see the manual valve, but what it sees, for example, is this pressure related to this flow is now different. Or this control valve used to have this impact on flow or this impact on temperature, and it's no longer having that impact. Well, that's because a manual valve is closed. PCA won't tell you, hey, check this manual valve. What it will tell you is there's a relationship here that's very different. And it can help you get to the root cause much more quickly. Now, the demo that we're going to do is a pump. We're going to characterize a pump rather than a large system, just a small system. And we're going to try to determine if it leaves its normal operating regime. Again, to save time, I've pre-built my trend. The order in which you put the tags on the trend does not matter for PCA. They're all X's. Similarly, the reason I have two copies of the trend is the left-hand side is going to be the data that I use to build the PCA. And then the right-hand side, the time frame I'm going to use to evaluate my PCA model. So just like the PLS model, what we're doing at the end of building a model is we're not evaluating the system yet. We're not saying, oh, is the flow shifted or the VP a problem or is our pump different? What we're doing is we're trying to evaluate our model first. That's a very important step before it goes into production. So just like before, I right click and I bring up my PARCModel menu. And also just like before, I'm not going to change any of these settings. I'm going to use 1 minute interpolation, but instead of creating a new PLS model, I'll create a new PCA model. And like the PLS, it's using all of the data that was on that trend that you clicked on, the one on the left-hand side. So you see some of the similar information. We have our pretty colors with our concentric circles on the right-hand side, and simple me, I look at this and I say, you know what, every observation is inside those. I'm not going to touch that. That looks good to me. The second place I go is over here to our DMOD X trend. I haven't talked about the DMOD X versus the HT2M. This might be a good place to at least introduce those. Each observation is shown on these trends. So, you know, we've got 10,000 or so observations that are feeding into the model. DMOD X stands for distance of that observation, distance from that observation to the model in X space, meaning however many dimensions we have. And we have seven X's, so there would be theoretically 7 dimensions. You don't have to try to picture that in your head. We've got it in 1 dimension for us to look at graphically. And right here, the calculation says the distance of these observations to the model are a little bit higher than the rest. This red line here you can think of as the point of statistical significance. Once the observations cross over that red line on a D mod X trend, what PARCModel is telling you is, hey, these observations are starting to push the boundaries of whether they actually fit the model well or not. So, you know, observations that are kind of bouncing around here and even here may not be something you have to go get rid of, but just as a matter of practice, when I see something this high and it's really 2, 3, 4, 5 of these, I normally highlight those and I just delete them. And now I'm just doing it really because it helps the demo, shows you guys that when you delete it, I press the delete key again. When you delete it, it recalculates the model. So that's the D mod X. The HT2N, the hoteling t-squared normalized. This is not really showing you how the model is performing or how the observations fit within the model per se, but really how the observations fit within the bounds or the range of the different, of all of the different X's. So for example, it looks like there was a period of time here, somewhere around observation 6,000 to 6,200, where the system, something in the system, maybe multiple X's, maybe just one X, were significantly different in range from all of the other periods of time before and after, okay? But if I see a high HT2N and I go up and I don't see a high D mod X, then what that says is, okay, even though there were some parameters that had a very unusual range, okay, their D mod X, they fit within the model just fine. So sometimes it's okay to leave a high HT2N set of data in there because what you're doing is you're leaving the range of your data expanded. A reason to do that. Let's say your model, one of your X's is a production rate, and the model set models production rate between 500 and 800. But really there was only one day where your production rate was over 750. So that might look like this right here. You know, PARCModel might flag it and say, hey, you had this one day of unusually high production rate. But if it fit within the model, I will usually leave it there. Okay, I'm happy with my model. I've removed a little bit of D mod X data. I'm leaving the HT2N alone. I saw nothing over here to remove, so I'm going to save. And because this is a system, you would, name it after the system. So I'm going to call it, pump 215 or 216. I'm going to give it a model. I'm going to say this is my version 1 because I can have multiple versions. I'm going to set as active model again. It's the only one. And I'm going to continue. And just like the PLS, it's now saving the PCA and it's creating all of the tags that are necessary to evaluate the PCA model. I can close PARCModel now, go back to my PCA trend. And what I'm going to do in order to evaluate my model is I'm going to add a couple of trends at the bottom. I'm going to go to a 2x2 here. And on the right-hand side, I'm going to drop my D mod X tag. And on the left-hand side, I'm going to drop my HT2N tag. So remember, I make sure I'm in my PARCModel source and I click refresh and the number of tags changes because I have a new model. I named it pump 216. And right here at the top, I have my D mod X and my HT2N. Now remember, if I just, let's just look for D mod X real quick. I want to make sure that this is clear. There are 2 D mod X tags. Remember, there's one for my version 1 that's specific to that version, and then there's one that is specific to the project name so that I can create multiple versions and have one version active. This tag will always be based on the active model. So this is the one that I want to look at. Now I'm going to get rid of my D mod X filter and put the HT2N on the left-hand side. And we said that we wanted to evaluate on this time frame. So I'm going to drag my time frame down here, drag my time frame down here. But what is it telling me? It's not telling me anything yet. There's another step that I need to do, which is to turn on limits. So when you click that continue button to save your model in the system, it's not just creating these statistics tags, it's also creating the limits based on the data that you fed it. So, and they're always control limits. So you turn on the control limits. We can see that we've got some instances where the d mod x has gone above the control limit. And I can do the same thing with my HT2N. I right click and I turn on control limits. And I'm going to rescale these guys so I can see a little bit better what's going on. So my HT2N really doesn't have very much data that's gone above. So remember what we said about HT2N. That describes when an x or multiple x's have gone outside a range that the model is comfortable evaluating. So why don't we just investigate that very quickly. I'm going to turn on markers. And I'm going to put a marker in one of these red areas where the HT2N has gone too high. Now, if I right click on the marker, you see there's a menu that comes up that's context sensitive. It sees that I have the HT2N tag on here with the limits on here, and it says, hey, you're looking for the contribution plot. That's exactly what I'm looking for. I want to know the top contributors to that deviation in HT2N. So it takes all of the x's and it says, okay, for that very specific point in time, at that moment, the HT2N was this number, and here's what was contributing to the HT2N. Well, right here it says total dynamic head. If I left click on that bar, I get a trend of the total dynamic head. The blue is the actual total dynamic head. That is what's coming from the historian. That's what the pump was actually producing. The green pin is the X predicted value. This is the value that, based on what all of the other X tags were doing, what the model thought the total dynamic head should be doing. And you can see right here where my marker 1 was placed, the actual total dynamic head continued to drift down, 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 lower and lower. And the green pin says, well, you know, when I'm looking at all of the other X's here, I don't see a reason to believe that it should be dropping. It changes enough, it deviates enough that it says, hey, I've actually got a significant deviation. But what we're looking at is the HT2N. So HT2N tells us that it deviated from the base data. So that's why I want to look now up here. There's dynamic head. This is my base data. This is my evaluation data. So if I turn on quick statistics, the minimum total dynamic head was 923, okay? But if I turn on Smart Mouse over here, I can see my total dynamic head was getting down under 700. So that is the reason that this has gone above the limit, so to speak, is the model is basically saying, you know what, I'm okay with the total dynamic head getting to a certain point below 923, but once you get down too far, I'm going to start saying the extrapolation is now questionable. So the HT2N is telling you about range. Now what about the D mod X? There's a lot more red on the D mod X. We do the same thing. We can turn on markers and we can investigate what I'll term as events, these events. And we're not going to investigate all of these. I'm just going to use one as an example. So we look at this guy, we right click, and you can see the context menu has changed. Launch D mod X contribution plot. And he's saying, hey, the temperature is way off. Now remember, DMOD-X is not looking at range like HD2N is. It's looking at the difference between the actual and the modeled. So if I left click on temperature, we see something similar to what we saw with the total developed head. The modeled temperature is green. The actual temperature is blue, and it's way up here. And it's the DMOD-X is actually flagging this delta and saying this is so severely significant that it's statistically a different system. So now, as you're building your model, you might want to back up and just take a look at the whole trend. You look at the shape of both of these lines, and they don't look anything alike. The temperature, the way the temperature actually moves doesn't seem to be reflected in the predicted temperature at all. So that may be an indication that temperature doesn't really play a role in diagnosing a pump, which it really shouldn't. The temperature of the liquid, in very rare cases, unless you're cavitating, shouldn't affect how the pump is performing. So what you can do is remove temperature from the model. So I'm going to close that trend. I'm going to close my contribution plot. You can right click on any trend here, and I'm going to bring up my PARCModel window again. But this time I'm going to go to this list of projects. I'm going to open up a saved model. So this already has the data cleaning that I've done in it. It's exactly the model that I saved earlier. I can open this saved model and I can say, you know what? I don't know why I put temperature in there. I'm trying to characterize a pump. I'm not trying to characterize a pipe. I can go down to temperature, and just like I did with specific gravity in the PLS model, I can exclude the variable. It dynamically calculates a new model. I can save this. And this is where I start adding maybe descriptive. V1 hyphen no T, or no temp. We'll say no temp. Continue. And I can close PARCModel. I'm going to delete these tags because that's version 1. I can remove my markers for now. Let's go back to Tag Browser. Remember to refresh. Pump 216. Now I'm going to drop the same project name, not model specific, but project specific. And it's calculating differently now. It's calculating from the new model. I turn on my limits. What I'll immediately see is, even though I still have quite a bit of red, this giant jump up that was here at the very beginning is now more just chatter. You know, above the limit, back below, above the limit, back below. For me, that's usually not a concern at all. And I really only have maybe 1, 2, 3 events to investigate further. I guess I should turn these back on. And then the process for evaluating the model continues until you feel you have a good model that all of these deviations, all of these red areas, are actually significant process changes that you would want flagged. So that is the end of our PCA demo. I'm going to close the trend. Not going to save those changes. And it's time to ask some questions.
Hello, Richard. Thank you for that wonderful presentation.
Hey, Adam. Thanks.
So far, we haven't gotten any questions in the chat, so I'm going to ask you a question or two that I thought of as things were coming up. One, how would you say that our PARCModel tool compares to other modeling tools that you've used throughout your career?
Oh, well, that's a That's going to seem like a planted question. I haven't used a whole lot.
Okay.
I did the simple stuff in Excel, but as far as other tools that would even approach this kind of complexity or have a differentiation between PLS or PCA, that kind of thing, I didn't really use anything before PARCModel, so I really don't have I wouldn't say I don't have anything on the same plane to compare it to.
Okay. Yeah, I feel pretty similarly. I hadn't really used anything else before, but I found PARCModel to be surprisingly, once I kind of got in there and had a little bit of guidance, to be pretty user friendly and pretty powerful. And I think you exemplified quite a few of those ways in your presentation. The second question I have for you is, kind of in your day-to-day, given that you help monitor some processes and help control things, how often are you looking at the results of these models? So not configuring them kind of like you showed, but how often are you looking at the results and using that to make decisions?
Well, yeah, I guess when I was working in industry and I was I was sort of the end user, I would say probably looked at it at least once a day, but would prefer to set up alarms to, for exception notification, rather than have to go find it and convince myself that everything's okay. I'd rather have something when it's not okay, tell me. But in the consulting version of my role, it really depends on the customer. So for example, one customer had 15 batch digesters that they had done phase modeling on. So 3 different phases across all 15 digesters. And we had they had a daily or 3 times a week meeting every morning to go over all of the statuses of all of those models. Again, only the ones that were flagging something. These were PCA models. But a PLS model, I really didn't interact with necessarily on a daily basis as far as looking at the stats or anything, but the final result was something that you could argue that I used every day. For example, if I had to model a flow, because the flow meter was only good in a certain range, but the actual flow moved outside that range quite regularly, well, I would have to use that in a mass balance. Well, then once it gets wrapped into a mass balance, I'm actually using it every day. I'm using that every day, or at least I'm relying on it every day because it's part of a mass balance. So, yeah, I think PCA you interact with more often. PLS, maybe that's a danger point, is you just come to rely on it. Once you build it, you're done. So you probably should, put some alarming or some alerting in there if there are some deviations that would indicate that the instruments you built the model on might be having problems.
So we did get a few questions in the chat. So this kind of transitions nicely to one of them, which is how would you go about putting an alarm on a PCA model? What property would you want to put that on, or do you have something in mind that you like looking at?
Yeah, for me, it's definitely the DMOD-X normalized tag for the model, because for me, that's when the statistics or the math or the numbers or whatever, however you want to think about it, that's when the model is telling you this system is actually a different system than the system you modeled. Like something has changed so significantly that mathematically this is a different system. So things that can happen in real life like that are like closing a manual valve or an instrument going completely offline, whatever. And sometimes those things are very obvious, like when an instrument goes offline. But when a manual valve closes or opens or whatever, that's not always immediately apparent, right? Because it's out in the field.
Right.
The HT2N, I don't necessarily alarm, but if it goes outside its limits, the HT2N statistic for the model, if it leaves its limits, really all it's saying is, hey, Richard, I don't have a good solid mathematical basis for telling you that this model represents your system. It's almost like starting to hint to you saying, hey, you've moved into a production rate that's so far outside what you showed me when I built this model that I'm no longer comfortable telling you the model is okay. And then I sort of look over at the DMOD-X, and if the DMOD-X is still within its range, that means the model fits, the model still works, but the HT2N is telling you that might just be luck. or that you've got a really good model that can extrapolate, which is not always the case. So I don't normally alarm the HT2N. It's something that I would look at maybe, once a week or something. But the DMOD-X, depending on the criticality of the process, that's what I would alarm on.
That makes sense. And the way that I've always heard it phrased is, you sort of create a model space, and DMOD-X helps you let you know when you sort of left that model space, if you will. So yeah, that makes sense. Okay, we got another question in. Are there any plans to go further than linear models? And I have an answer for this if you don't, I think.
Yeah, I don't know the plans, but I showed you in my PLS example how I get around the linear. I create calc tags that are nonlinear, like a square root of dp. That's not linear. So if I need to model something nonlinear because I know there's a square or I know there's a square root, I just perform that before I feed it to the model. But I don't know anything about the back-end engine plans.
Yeah. So I can speak to that. Right now, there are no current plans in order to move past that, or to move beyond or sort of further than linear models. We found that this covers sort of 95% of the cases. And kind of like Richard said, if you know what you're looking at, or you kind of know the nonlinear relationship, you can just translate it with a calc tag to get it there. But if we were to find that there's more ask for it, there's more usage, we can certainly look into putting that on the development roadmap if we want. Okay, and then one last question. Let's see. How long would you say it takes you to complete a small batch process, sort of modeling from beginning to end, so people have an idea of the relative effort?
Yeah. So if the batch process we're talking about is a single reactor or a single vessel rather than an entire plant or something like that, I can say in my past experience, a single batch reactor, 3 phases for PCA modeling, and I want to model two seasons, summer and winter. It would probably take me from start to finish 2 or 3 hours to have that model up and running. I might find after that point that I've got some tags in there that I shouldn't be. Or I've overweighted one of the components. For example, I used 4 pressures that are all very tightly related. I need to get that down to 1. That kind of stuff happens after, but I would say start to finish, you identify the tags, you build the 3 phases, you pull in the data, you build the models. Yeah, 2 or 3 hours, you can have 1 reactor done.
So pretty reasonably fast. And then, like you said, there's refinements and things, but that's enough to certainly get it up and running.
Yep.
Okay. Well, it looks like we don't have any other questions. I don't have any other questions for you. So we'll thank Richard for his time and appreciate the presentation. And I always enjoy learning more about PARCModel. It's one of the ones that I don't always use very often. So I really appreciate information like this.
Yep. Thanks, Adam.
Alrighty. And let's see, we will be back in about 10 minutes or so for our next presentation from Wayne. Oh, that should be exciting.